Okay, our last speaker of the day is Andrew Ilyas. He is a postdoc currently at the Stanford Statistics Department and is an incoming professor at CMU. He's going to talk to us today about predicting and optimizing ML training.
Yeah, thank you so much, Sasha, and thank you everyone for sticking around until the last talk of the day. This is joint work with some amazing collaborators at MIT and Google. Logan Engstrom, who is graduating right now, Benjamin Chen, who is graduating right now, very impressively from undergrad, Axel Feldman, Billy Moses, and Alexander Madry. The paper is on arXiv as of just a couple of days ago. So accordingly, this is like the real first talk I've given about this. So if I make any mistakes, feel free to raise your hand. OK, so the motivation behind this talk is that when you're training machine learning models, you have to make a lot of design choices. Right? You need to decide what model architecture you're going to use, and what size. You need to decide on some hyperparameters. You need to decide on a training data set. And making the right choice in each of these cases is hard. And so as a community, we've developed a bunch of tools to help us answer this fundamental question of how do we both predict how our models are going to behave as a function of these design choices, and also make these design choices optimally or close to optimally or the best we can. Right? So instances of this are programs for neural architecture search, scaling law research for figuring out how big our model should be, and various data selection methods. OK, so the dream would be to have one single framework that can magically make all of these design choices for us and predict the effect of making any of these design choices and so on. And this is the dream that is going to motivate this talk. How far we get, I'll let you guys judge. OK, so just to make things a little bit concrete, let's think about training data. And training data is nice because there's both an optimization problem and a prediction problem. So on the optimization side, we often care about curating training data sets. So we start with scraped internet data. We pass that into a model. And out pops our favorite language model. But within the scraped internet data, there's both super high quality good stuff that we want our model to train on. And there's also maybe slightly less reputable sources. And there's also just pure garbage. Right? And so a big part of any large model training routine is actually filtering the scraped internet data or curating it somehow into a pre-training data set that we then pass into our model. Right? And this is the problem of data set curation. And stated as an optimization problem, the question is, can we optimize the training data selection for some desired model performance, usually test perplexity or something like that. On the other side of things, on the predicting side, there's this problem of training data attribution. Right? And here, again, you have a model. The model makes a prediction. And let's say the prediction is totally wrong. And we're often interested in understanding this wrong prediction, or even a right prediction, somehow in terms of the training data. Right? We'd like to be able to point back to some training data and say, this part of the training data is what caused you to make a wrong prediction here. Okay? And I'm going to frame this as a prediction problem. Right? Because what you're really asking for here is, can you predict how changes to the training data would have changed your model's behavior? Right? Can you make statements like, if you hadn't trained on this in this example, you would have actually gotten this picture of a plane correct. OK. Before I move on to maybe giving a slightly more formal version of this vague problem statement, is everyone clear on what I mean by predicting and optimizing model behavior? High level. I see some nods. Yes.
Not exactly related to that, but a few slides ago, you had not only training data selection, but things like neural architecture.
Yeah.
And I was wondering what your impression of how successful have those things been in the past, and then what's your explanation for why they haven't been more successful?
That is a great question. I'm going to ask you to ask me that again, maybe in a couple of slides, because hopefully the next little bit will answer some of those questions. Yes.
This is very cool. So from my understanding, there are two kind of related problems. There's the how does this piece of training data affect downstream performance, and if I want some desired performance, what should I change to my training data?
Yeah.
Which problem are we interested Or are we interested?
We're interested in both.
Okay.
We're interested in like the silver bullet that can predict perfectly and optimize perfectly. Okay. So now I want to sort of give a more general problem statement that goes a little bit beyond training data into this like vague problem that I'm going to call, or the high-level problem that I'm going to call meta-parameter selection. Okay, so the idea here is that I'm going to represent whatever training choice I'm interested in studying. So that could be the data set, but that could also be the architecture or anything else as a variable z, okay, that I'm going to call a meta-parameter. Then I'm going to fix a training routine A that maps from a value of this meta-parameter to a trained machine learning model. Okay? So the output of this is just going to be some parameters of a machine learning model theta. And everything else other than z is fixed within this algorithm. So if I'm not optimizing hyperparameters, then the hyperparameters are part of the algorithm, for example. Finally, I'm going to specify an output function phi. And that output function is going to be a map from a machine learning model to a real number. So this you should think of as like your loss function or your prediction on a specific example or whatever outcome you're interested in predicting or optimizing. Okay, and we're going to represent that as phi. Okay, and so the final output of this pipeline is going to be like phi of a of z, which is really just this like metric of interest evaluated on a model trained with whatever meta parameter you chose. And we can sort of rewrite our two goals here more generically as follows. We're going to call optimization this problem of finding the optimal metaparameter z to minimize this output function phi. Okay, so you should think of this output function, for example, as being like your loss on some target data set. Maybe z is some representation of your data selection. And the optimization problem is to, the optimization problem is to find the z that minimizes your loss on this target data. Then we're going to frame a prediction problem as finding some surrogate function f that maps directly from the metaparameter z to the output of interest. Okay, so in the case of like data attribution, z here is like which examples do I delete from my training data? And what I'm after is a predictor of if you remove these examples from your training data, then this would be the model's prediction on this example. Okay, and the goal here is to capture not just data attribution and selection, but also just broadly a bunch of optimization and prediction challenges in machine learning. Okay. I think this is like probably, if you remember one slide, or if there's one slide that's important for the rest of the talk, it's probably this one. So if there's anything not clear, now would be a fantastic time to ask. Yes?
Metaparameter before training.
Yes. So the metaparameter is some training quantity.
And so then in the optimization case, what if I choose the test set?
Great. Yeah. So that's not going to be captured here. The test set is going to be wrapped into this function phi.
So there's a constraint on which z I can choose.
So in this case, I guess in the setting you're describing, you would encode the test set into this function phi. And z would, for example, be... Oh, are you asking if z can be the test set?
Like I want to minimize loss on the test set, right?
Yes.
I could simply train on it.
You could. But ideally, for example, you want to minimize loss on some test distribution. So you can pick half of that test distribution. You can sample from that test distribution, encode it into this function phi, and then test on some completely new test.
So I can't choose z arbitrarily, right? So there are some constraints for what I can do over there.
Like in this framing, we're going to let you do whatever you want to z. Whether the end thing ends up being useful for your task is kind of a function of whether you designed this properly.
Just a follow-up. If you given the test sets, can you choose your training data sets to be somewhat aligned with your test sets?
Yeah. So in this framework, you absolutely can. So if you wanted to do that, you would wrap your test set into this function phi. Like this function phi would evaluate a model on your test set of interest. This algorithm A would be training. This z would represent the training data set. And then this would exactly correspond to finding the training data set that minimizes loss on your test set.
But would that be trivial?
That would be a very bad thing to do in general, because you would end up with just something super overfit or something like that. So in general, you'll want to do something smarter. But as I've presented it so far, this is just an arbitrary function.
But in your framework,
Yes.
You want to minimize the loss.
Yes.
So you should choose the training data to be equal to your test set, which is where
Oh,
I'm at.
yes. Yeah. Sorry. So in general, yes, you could just make this training, that would just not be a very interesting optimization problem to solve, is what I'm saying. Conditioned on defining an optimization problem, these are our goals, but some optimization problems are just not very interesting, such as design an exact training data set to minimize loss on the test data. You'll just reproduce the test data.
Okay.
Yes.
It seems like a key part of the goal here is that you want the predictor to not be too expensive. Because of course you could just invoke A, you say don't do that, but I could also just train an almost A thing.
Yeah.
And then go through some expensive procedure to get almost exactly the right.
Absolutely. Yeah. So in reality, we'd probably want to qualify this and say does not invoke A and is also much cheaper to run or something like that. We want something reasonably inexpensive here.
Yeah. So I'm curious if there's a nice formalization of that constraint of being much less expensive than.
Yeah, we've thought a little bit about it. I'm happy to talk more about it offline. In general, you can actually think about pre-processing time for computing this function f hat, and then once you've computed the function f hat, you almost want the predictions themselves to be very fast to compute. But it ends up being a little more complicated than just some kind of wall clock time thing.
So going back to the question of the test sets being exactly the same as the train, why not, like you said, it won't be an interesting optimization problem, so why not exactly encode it? You can select any data that is not the same as the test data.
Oh, yeah. So in general, we will make this problem interesting. The only point of this slide is to introduce the general framework we're operating in the same sense that I don't know, I could say this is x, this is f, and then this is f of x, and we just want to minimize f with respect to x. Yes.
So just to make sure, both functions a and b are fixed, right?
Yes.
Fixed mapping?
Yeah.
Okay. We're only just changing the input.
We're only changing z. Okay. So just to illustrate how this problem might work in cases that I think are more interesting than directly optimizing the training data, we can, for example, try to do data selection. Right? So if we have some fixed training data set and we want to filter it, we can define some training set dimensional vector z that's going to weight the losses of the individual training points. So for example, z will have dimension equal to the number of training examples. If it's 0, that means we don't train on an example. And if it's greater than 0, we'll train on an example and multiply its loss by zi. Our algorithm A will just be a model that's trained on the selected data. So we can threshold z, train a model on the data we actually selected, ignore the rest of the data. And our output will be, for example, the loss on a specific fixed target task. Okay, and this is what data curation is going to look like. And we can do a similar exercise and express data attribution in terms of this framework. Okay. So the rest of this talk is going to be organized in roughly 3 parts. The first part, which is probably the most important, is the main solution concept, the main idea that we're going to introduce, which is called the metagradient. We're then going to sort of go back a little bit and talk about how we actually do the first part. And then keeping with the theme of this workshop, I'll maybe talk a little bit about what I see the future as. OK, so let's start with the main idea. And I've sort of abbreviated the notation that we've been using so far here. We have some training setup, which is just a metaparameter z. We have a trained model, which is just a learning algorithm applied to that z. And we have a model output, which is some fixed function phi applied to the model. Our first observation is that in a lot of cases, but not all, we can express this metaparameter z as a continuous variable. Right? So we can do data selection, which is this very discrete thing, but we can also weight data points. Right? And that's a nice continuous thing where we can make our z real valued. And so based on that observation, we're going to show how to compute something called the metagradient, which is going to be the gradient of this final model output with respect to the initial sort of pre-training metaparameter z through the process of model training. Okay, so this is like a gradient of a super long, super expensive operation. And the cost of computing this metagradient, and I'll talk about how we actually do it later, but the cost of computing this metagradient is going to be roughly 3 to 5 times the cost of just training the model. Okay, but before I talk about exactly how we do this, I want to sort of go through what this enables, maybe quantitatively. Okay, and sort of the takeaway of this part of the talk is just to argue that metagradients offer a pretty general framework for optimizing and predicting, at least a couple of aspects of the machine learning pipeline. Okay, so let's start with optimizing. Remember, our goal here is that we have some design choice, whether that's data selection, whether that's pixels of individual data points, whether that's hyperparameters. We have some design choice, and we'd like to make it optimally for downstream model performance. So our general recipe is going to look like this. We're going to write our problem in terms of sort of this notation that we've been talking about. So we're going to decide on a specific z, a, and phi so that our design decision can be expressed in this form. So that what we want is to minimize with respect to the meta parameter z, the model output evaluated at z. Once we've done that, we're just going to solve with gradient descent because we have the gradient. So we're going to pick some starting meta parameter z0 and some number of steps. And then at each step, we're going to compute the metagradient, which is, again, the gradient of the final output with respect to this pre-training quantity. And we're just going to take a gradient descent step. Right? And we'll do this t times. So the total cost is going to be like 3 to 5 times t times the cost of training a model. And that's it. That's the whole recipe. OK, so what does this look like concretely? Question? Yeah.
You're going to have to do some implicit differentiation or something.
Great question. There's going to be no. This is going to be totally exact. There's going to be no implicit differentiation.
I'm very curious then.
OK. So let me first give you some of the applications for people who are less curious about differentiating through optimization. OK. Data selection. Remember, the goal here is, in general, you pick some training data set, you train a model on it, you measure your loss on some target set, and your goal is to find the subset of the training data that's going to minimize this target loss, right? In expectation, not on a specific target, not on a specific finite sample set. We want to find a good training data set for this target task. Okay, so an equivalent way to say this, and one point that was made in a talk yesterday, is that an equivalent way to think about is that we want to find the training data weighting, the weighting of the training data points, that's going to minimize the loss on some target task. Oh, OK, sorry. OK, and I guess I don't need to say this based on all of the talks that we've seen so far, but this is like an increasingly important part of large-scale training pipelines in general. People are like super secretive, super protective about what data they actually train on. OK, so what's our approach? Our meta parameter z is, again, going to just be a vector that's in the size of the training data set, where each element of this vector is going to be some weight that we're going to put on the ith training example. The learning algorithm, in this case, I'm going to look at clip data selection. So it's going to be like a standardized sort of training routine off the shelf that we're not going to change. Finally, the output function is going to be some loss function evaluated on a bunch of target tasks. And I'll give the exact setup on the next slide. And our algorithm is going to be as follows. We're going to start from z equals the all ones vector, which is just training on all of the data. We're going to train a model by weighting the training points by all ones. This is just standard model training. We'll compute the metagradient. We'll update with the sign of the gradient to make sure that z stays like integral. And we repeat this over and over again. OK, I made a slight simplification here. Happy to talk about it offline. It's mostly for efficiency reasons. But this is a high-level algorithm.
So the learning rate is 1.
The learning rate here is 1, yeah. OK. So let me quickly describe the setup we'll actually evaluate this in. There was this paper called DataComp a few years ago that basically proposed this challenge where they control the learning algorithm. So it's a benchmark. they control the learning algorithm, and they control the target tasks. And your only job is to curate the best possible data set. Okay, so this is like a public leaderboard. This is like the small version of this public leaderboard. Actually, there was a submission, I think, just yesterday or just last week. And the idea is that you submit a data set, they train the model for you, they evaluate the model for you, and then they tell you that you got 0.185 or whatever on this data set. Okay, so there are a bunch of submissions. I think there are 20-something in total. And the goal is just to curate a good training data set. And you can kind of see that over the last 2 years or so, the performance has gone roughly up from like 0.16 to 0.18 in this small task. Okay, and so if we just apply this gradient descent thing, what we'll find is that we can do a lot better at data curation, right? Just by like doing gradient descent on the data weights directly, we're able to find a new training data set that's given in green in 40-something steps of metagradient descent, which is just this sort of meta algorithm I showed you earlier. We're able to find something that is, don't want to misquote it here, 4 points better than the previous sort of state of the art on this leaderboard. And in fact, like the difference between the data set we find and the previous state of the art is about as big as the difference between the previous state of the art and just not filtering at all. So we're able to make a pretty significant gain. This is on the small version of this benchmark. We're running the slightly bigger version, whatever our academic budget allows for. We're already #1 there, and we'll see where it ends up after however many steps we have to run. Okay, the second setting we can look at is selecting instruction tuning data. So this is another sort of standard data selection setting where you have a bunch of instruction tuning data sets for a large language model, and your goal is to make a good instruction following agent. And here, our baseline of comparison is going to be this paper, which for some reason the citation did not animate for. But this is a paper from Xie et al. From Sanjeev Arora's group. And so the baseline method called less sometimes improves performance, sometimes slightly hurts performance. But by just doing gradient descent on the weights of the instruction tuning data, you can find an instruction tuning data set that consistently helps performance. Yes?
I'm curious about, other than the number increase, do you have any qualitative explanation for why performance increase?
Yeah, that's a good question. So I think more so on CLIP, you can kind of see that there are a bunch of tasks that, like basically all of the methods, all of the methods here, most of them are usually involve some kind of heuristics, and those heuristics just can't improve the performance on some of the target tasks. So a lot of the gain seems to be from for these target tasks where there aren't great human heuristics for how to select data, we can improve performance a lot, and that ends up affecting the average.
What's in the data comp setting? What's the data you have access to, and how does that compare to the training data and the final thing?
Right. So they give you some small subset of, I think it's Leon or something, some large data set, and they ask you for basically the indices that you want to train on. So your goal is to select a subset of those indices. But the sort of pre-training corpus is some web scraped data. And the target tasks are standard zero-shot, ImageNet, CFAR10, food, chameleon, wilds, all of those things.
So your method will give a value between 0 and 1 to each of the data points?
Yeah. Well, yes.
And what will that distribution look like?
Yeah, that's a great question. So we actually, I have plots of it that I can maybe show you afterwards offline. It's probably easier. But in general, actually the method sometimes assigns weight higher than 1 to some of the points, which usually just means repeat them. But it looks pretty normally distributed. There's nothing super crazy. Yes?
So the methods that you're comparing to here, how computationally expensive is the Metagradient approach to the baseline?
That's a great question. Unfortunately, the code for a lot of the baselines is not actually available because all you have to submit is the final data set itself. I will say that in general, I wouldn't take this as evidence that like we should throw away, that we should like start using this right now for data selection. And I'll talk about this more towards the end, just because like the compute that you use, and this is generally true of like data selection methods, the compute that you use to do the data selection is often non-trivial. And here, I mean, 40-something, or I guess you could get away with like 20-something metagradient stuff basically means training the model 20 times over, which is often not great for performance. The exception to that is actually here, where like even if you keep training for longer and you like sort of are compute unconstrained, it's actually sort of hard to improve on training on the full data.
Yes. Do you need full access to A and phi?
Yes. So here we're assuming complete access to A and phi. Yes.
One thing that I'm confused about is like, to what extent are you training on the test data?
Oh, that's a great question. Here, like the selection is done for a validation data set, and the evaluation is done on a separate held-out test data set. So you're not you are overfitting to the task, but that's the goal here. So like, I'm targeting some subset of the data set. I do metagradient descent targeting that subset, and then I evaluate on a totally held-out set of samples.
Well, like in the datacom thing, you're submitting the data indices, so it's exactly that data set that gets used for training.
It's exactly that data set that gets used for training, but the targets that we're selecting for are not the targets they're evaluating on. Like you're not.
Like the model is different, or the optimization procedure.
No. So oh, okay. Are you asking about overfitting to the data or to like the algorithm and stuff?
To the test task, like.
Yeah. So like the goal here is explicitly to fit to the test task. Like you're trying to get a clip model that's really good at ImageNet, but you're not like fitting to the specific. You don't get to see the specific ImageNet samples that you want to be good on.
Okay.
You just get to see some ImageNet samples, and then you can try to be really good at those, and then you can see whether the model you get is good on other ImageNet samples.
For the competition, you submit your subset of indices and they train the model themselves?
Yeah.
So you know in advance what's going to be the training algorithm?
You know in advance the training algorithm, and you can actually run it yourself, but you don't know exactly what, like they're going to evaluate on some slightly different.
But can you set the hyperparameters like learning rate?
No.
They are telling you which...
All of that's fixed and known, yeah. Yes. Last question.
Sorry. Do you get like meta hyperparameters? Like now you have the learning rate of the meta optimization procedure.
Yeah, so here it's set to 1, just so that the z always stays as an integer. But in general, yes. And actually the next application there will be.
Thank you.
We're going to move on unless there are more super pressing questions about data selection.
We want the punchline, though.
Sorry?
We want the algorithm.
Oh, the algorithm's coming. The algorithm. Usually, okay, this is the opposite problem I usually have, where people don't think it's that cool and want to see the applications. One more application, then we'll get to the algorithm. Okay, so this application is one I am personally super invested in, and it's this setting called indiscriminate data poisoning, where you start with some training data set, and your goal, you're an adversary in this setting, and your goal is to insert some epsilon fraction of training data so that the final model that you train has really bad overall test accuracy on whatever distribution you trained on. Okay, so I'm like training on CIFAR 10. I want to insert some small number of training images so that when I train my model on CIFAR, on this like poisoned data set, I do really bad. Okay, so say that as an optimization problem, I'm trying to insert data points that maximize overall test loss. And speaking from experience, and from this really nice paper by Yue, Gautam, and Yaolang, Yuwaru, in this like indiscriminate data poisoning setting, it's really, really hard to poison neural networks in this way. Like generally speaking, if you insert an epsilon fraction of poisoned data, for a really long time, I was convinced that like the best you could do was an epsilon degradation in accuracy. And this paper from Yue got like slightly better than epsilon degradation accuracy, and I was like super, super happy about that. So, okay, what's our approach going to be? We're going to, again, just frame this as an optimization problem. Our meta parameter now is going to be the pixels of epsilon times n training data points and their corresponding labels. The algorithm is going to be just standard CIFAR 10 training with a deep neural network. And the output function is going to be loss on a held out validation set. Okay, so we're going to like keep part of the CIFAR 10 test set separate. That's like for the adversary. And we're going to evaluate on the other half. Okay, and this is our algorithm. We're going to train a model, replacing the first epsilon fraction of the training data with our meta parameter z. Right? So we're optimizing over these epsilon n Poisson points. We're going to take those epsilon n Poisson points and just replace the first epsilon n points in the data set by whatever we're optimizing. Then we're going to train a model normally. We're going to calculate the metagradient, and we're going to do this update. Okay, and this is actually not simplified now. This is just the full algorithm. And we're going to repeat this over and over again. What do the results look like? This is the algorithm from Yue, Gautam, and Yaoliang at Waterloo, which is the state-of-the-art algorithm before this. And poisoning, I think, 2% of the data set, they can degrade accuracy by 0.8%, which again, it doesn't look like much, but this is actually, it's really hard to do even this. But by just doing gradient ascent on the actual pixels of Poisson training data, we can drop the training performance by 14% or something like this. Questions about this application? Yes? Oh, great question. So this is not an attack that's happening at test time. This is not, these are training images that are being fed into the training data set. The model is training on them and then doing poorly on natural, normal test images.
Right, so all of the backdoor attacks are similar, right?
So the backdoor attacks are targeted, right? So they require you at test time to insert a backdoor of some kind. Here, I'm trying to do very poorly on normal, clean test images. And this is actually this quote, This quote that I was showing from this paper was actually contrasting this indiscriminate setting to the backdoor setting, where the goal is to basically kill the model's accuracy on a very specific subpopulation of examples, such as the subpopulation with a backdoor or something like that. Yes?
How detectable do you think these poisoned...
Right now, super detectable. I mean, if you looked at this, this is not a frog. I don't know what to tell you. This is probably not a deer. It's super detectable. I think if you explicitly tried to optimize for undetectability, you could try to do something. But for now, this is just we're just trying to maximize the test loss. Question back there.
Can you limit yourself to select only images where the labels are correct, but still would make the accuracy go down?
Yeah, so one thing we've tried doing, with actually some success, just not as much success as this, is not optimizing over the labels and just trying to change the images and make them not change that much from the original training image. And there's some stuff you can do there, and the accuracy does degrade to 80-something%. But in general, this is a really costly procedure. This is training a CFAR model 800 times. So we did not super optimize this very much at all. Yes?
Does the accuracy degrade for certain labels, or does it degrade kind of uniformly?
It tends to grade pretty uniformly across all the labels. Yes?
Is there not just for this example, but in general, is there a lot of transfer where you can do this training for a much cheaper thing and then it works on much more expensive?
Yeah, we actually didn't really try that here, except in one very special case that I'll talk about at the end. But I think in general, to make this practical, we'll have to somehow make it transferable if it's not. And for data selection in general, there's some evidence completely separate from this paper that doing data selection for smaller models can help bigger models and things like that. But that's a totally separate investigation from what we're doing here. Yes?
The original model, I might have missed it.
Oh, the original model here is just a ResNet trained on the CFAR data set.
I see. And do you think, let's say I can differentially private and this type of robustness technique, this wouldn't work too?
Yeah, I think if you tried any reasonable defense here, this probably wouldn't work. I think to make something that's maybe robust against defenses, you would have to do this metagradient descent with the defense in the loop somehow, an adaptive attack. Here we're considering the most basic case, which is just standard model training and changing images. Okay, I will go super quickly because I said I would get to the algorithm. But so far we've been talking about optimization, and the only point I want to make here is that a very analogous thing holds for prediction tasks. So here again, we're going to sort of rewrite whatever prediction problem we have as a meta-parameter prediction problem. So we're going to pick a z, an a, and a phi. Then our algorithm is going to be as this. We're going to pick some like z0 that we're going to call a reference meta-parameter. And our predictor is just going to be this first-order Taylor expansion that we get from the metagradient. Okay, so the idea here is that if someone comes to me with some new meta-parameter z and wants to predict what's going to happen, I have this metagradient that I computed once, which is just the metagradient around this like reference metaparameter that I picked arbitrarily. And I'm going to predict what's going to happen on their metaparameter using a Taylor approximation. Okay, so what does this look like? Just to answer a question from earlier, this to me satisfies this like fastness criterion because I really only have to do one metagradient calculation at z0. And then any other z, I'm just going to predict using this single metagradient that I've computed. Okay. Just to say what this looks like concretely, hopefully this slide looks familiar from a little earlier. But we're now going to look at sort of the prediction counterpart of data selection. Right? So now instead of picking a training data set to minimize some loss function, I'm going to pick a training data set, train a model, see what happens to a specific test example. And my goal is going to be to predict the effect of dropping some of these training samples on my model's prediction on this test example. Okay, so we're going to go through kind of the same logic as earlier. We're going to rephrase this goal equivalently as trying to predict the model's loss on this test example as a function of some weighting that I'm going to put on these training examples. Okay, and this problem has been super well studied throughout the literature, and I'm going to compare to sort of two state-of-the-art approaches for this data attribution problem that actually manage to sort of like pretty moderately correlate with how models actually behave as a function of the training data. Okay, so what's our approach? Again, metaparameters is the data weighting from last time. Learning algorithm is a standard training routine. The output function now is going to be a loss evaluated on a specific target example. And then what I'm going to do is I'm going to train a model on all of the data, which corresponds to sort of applying to the L1s vector. I'm going to compute this metagradient once, and then I'm going to use a Taylor approximation. Okay? And for people familiar with this, this is actually super well studied. This is called the exact influence function approximation. Okay? So people have applied influence functions before. The standard way of applying the influence function is to estimate this via implicit differentiation. You can view this as like exactly computing the influence function approximation. Okay. So what happens here, if we study, for example, deleting random 1% subsets from the CFAR10 training set and looking at the output on a single example, the way you should interpret this plot is each point here is a different training data set. There's a different set of 1% of the points that we decided to drop. The x-axis is what we predict the loss will be if we dropped those samples. And the y-axis is what the loss actually was when you drop those samples. Okay, and so you can kind of see that this method in orange is like super highly correlated with model behavior. And this is just using the metagradient like I just talked about. And the next best method is still pretty good, but not nearly as good. Okay. And just a final note before we start talking about the actual algorithm is that this doesn't just work for CFAR, but we've sort of scaled this up to like roughly 2 billion parameter language models, and things seem to be still pretty good. Okay. In case you're curious, you're not actually going to find these results in the paper that I showed at the beginning. It will hopefully be online soon, pending our edits. OK, so that was sort of the meat of the talk, well, the part of the meat of the talk, which was just introducing this main idea of the metagradient and hopefully convincing you that it's like a pretty general tool for solving these optimization and prediction problems. In the next part of the talk, I sort of want to go over like how we actually do this, because so far the procedure for getting this metagradient has been somewhat just magical. Okay. So before I do that, I want to quickly go over some sort of related work, because this is actually the idea of differentiating through optimization has actually been around for a while. There are papers even before this. But I'd say like one of the first papers that tried to apply this idea to like the deep learning-ish era was this paper by McLaurin, Duvno, and Adams. And the idea is that they managed to use something like metagradients in order to optimize the hyperparameters of the training of a pretty small neural network. And I think the largest they scaled was like a 4-layer network-ish. As another sort of question has pointed out, there's also been a sort of concurrent line of work on trying to approximate the gradient through model training via implicit differentiation. And this is going to be like a much more scalable but pretty coarse approximation to the metagradient. And generally speaking, neither of these approaches have really managed to like fully optimize large-scale training for whatever reason. And I guess one thing I should note is that like these are just representative works, and there's like a really long line of work on all of this. OK. So how are we actually going to compute the metagradient? There are going to be two challenges. One is going to be computational tractability, and one is going to be optimization non-smoothness. Let's start with the first one, computational tractability. OK. So what would be like this dumbest, most straightforward way to try to compute a metagradient? I'd argue it would probably be to try to just use automatic differentiation. So automatic differentiation is a really nice tool that lets us take the derivatives of any function that's defined as a composite function of a bunch of smaller operations. Right? So if I define some compute graph and I apply some operations one after the other, automatic differentiation basically lets me take the gradient of like the final one of these with respect to other variables in the optimization. OK. So maybe one insight we could have is that training a machine learning model is just a really, really long chain of these elementary operations. So why don't we try to just like backprop through this, right? Like we'll just like write out in PyTorch, we'll unroll the whole training into like 1,000 lines of code, and then we'll just call dot backwards and see what happens. The problem that we're going to run into here is that there are way too many of these intermediate steps for us to actually keep track of. Okay, like every time I, for example, take a gradient step to actually train my model, I'm introducing like a bunch more operations into this compute graph. At the end of the day, my compute graph is like terabytes big, and I can't actually do anything. Okay, so for the rest of this talk, I'm going to basically just think about automatic differentiation as a magical black box that can compute gradients of a function, that can compute gradients through any sort of compute graph like this with an amount of memory that scales in the number of edges in the compute graph. OK. So the next sort of innovation here, which was introduced in 2017, is this idea of doing stepwise automatic differentiation. Okay. And the idea here is actually pretty yes?
Can you just emphasize again why it's like the memory constraint that stops you to do this direct auto differentiation?
Right. So
what's taking up all that memory there?
Yeah, the idea is that you're actually, so like let's say this is z, or actually maybe it's even easier to illustrate here. Let's say this is your metaparameter z, right? This metaparameter is being fed into like some initial model state. You're doing an SGD step. You get a new model state over and over and over again. To now compute the gradient of this with respect to this z requires storing all of these steps in memory.
So that would be like you're storing your parameters for your model across like...
Yeah, not just your parameters, but also all of the metadata you actually need to compute the backwards pass as well. So it's just like totally intractable. No one even tries it. People do actually try this other algorithm, which I'll call stepwise AD. And the idea here is just that we can write this gradient of like this with respect to these early z's as a recurrence. Right? So if I've computed the gradient up until here, there's a pretty easy, if I've computed the gradient up until here, and I have this state, theta t, saved, pardon me, then what I can do is sort of do basically a single step of auto differentiation and propagate that gradient one step back through training. Okay, so if I've saved like all capital T states of my model on disk, then what I can do is basically like start here, load this from disk, take the gradient, save the gradient, throw this away, load the previous state from disk, propagate the gradient one step back, throw the state away, and do this over and over again. And I'm only ever sort of keeping one step in memory at a time.
This is a form of like checkpointing?
Yeah, this is exactly checkpointing, yes. If you're familiar with AD, this is going to be a little bit of review. But this is just checkpointing. Right, so the algorithm here is that I'm going to save all of the states, and then I'm just going to sort of go backwards through them one by one, propagate the gradient through each one. OK. So our algorithm is actually going to be a really simple modification to this that, again, if you're familiar with AD, is actually going to look really familiar. And if you're Sasha, is going to look extremely, extremely familiar. But sort of the insight here is to notice that the only primitive we needed to do stepwise AD is to be able to traverse the states from capital T all the way back to 1. And the way that we happened to do this was by saving every single state. But if we make training totally deterministic, then we can actually rematerialize states as we need them. So what that means is that if, in stepwise automatic differentiation, I save every state, and then I traverse through them backwards, what I can do instead is I can save every kth state, right? And so instead of, I don't save these two on disk, I don't save these two on disk, and so on, I just save every kth state. I start here, and when I want to access this state, what I do is I hop back over here, and I train for 2 steps deterministically. Okay, and so what this is going to let me do, if you sort of do the math, is the total number of states that I'm now going to have to save is going to be like capital T over K plus K in order to rematerialize the states. And so if I optimize K, this is going to get me to root T storage. But actually, if this is like a really large model, even root T storage is too much. And so what we'll do is we'll actually just recursively apply this within each segment. So what I mean by that is we will go through and we'll save every kth state. And then within this segment, we'll actually go through again and save every kth state. And then within the segments of that, we'll go through and save every kth state until our segments are of length 1. People familiar with automatic differentiation will probably know this is just recursive rematerialization. And if you do out the math here, the idea is that this is now going to get us to just needing to save log T states, which is super doable for most large-scale models, at the cost of basically doing T log T training steps. And one fun note about this is that this is actually pretty nearly exactly recursive having AD, which I just ran across this tweet from Sasha 6 months ago and saved it. OK. So that's basically it for challenge number 1. And this is how we're going to compute the gradient of the final model with respect to the meta parameter z. The final cost is going to be log T space and T log T training steps, which for the model sizes we consider is pretty doable. Okay. Any questions about this before I move on to the next? Yes?
What's the extent to which people do this in normal training?
Like the recursive rematerialization stuff? When training really, really big models, maybe a little bit. But I think in general, when you're training models, usually the most you do is just checkpointing. I don't think people go people usually don't root T or root number of layers, I guess, training, storage is not really that much in training.
That's because they don't want to trade off more memory.
Exactly. Here we're explicitly, we're super space constrained. In practice, usually not that space constrained, so you can get away with just checkpointing.
So your training is deterministic, right?
Yes.
But for example, in a datacom challenge, it might not be, right?
Yeah, absolutely. So in that case, basically what we're essentially running is stochastic gradient descent. Because we do multiple steps of this gradient descent, each step we're going to make training deterministic, but we'll change the seed between steps of gradient descent. Okay. Any other questions about how we compute this? In that case, let's move on to the sort of second and final challenge, which turns out to be pretty tough, because a gradient is really only useful in general if the function that you're taking the gradient of is smooth in some sense. Right? And given that the function that we're taking the gradient of is actually like this super long process of model training with some non-convex architecture and so on, there's not really a good guarantee that the function is going to be smooth and nice. I guess maybe I've like spoiled it a little bit because I showed you that we did all of these applications, so we managed to do them somehow. But if we just sort of look at the optimization landscape of a model output function with respect to, this is our data poisoning use case, so these are just like 2 pixels of the training data set. And we look at sort of how this model output function varies as a function of these 2 metaparameters, we see that the underlying landscape here is terrible. Like even if you could take the gradient of this function, you would not want to, because it would lead you nowhere. Right. Does the problem here at least make sense to people? Like, we want to take the gradient of this function. I just showed you this really long, complicated procedure for like, we're going to take the gradient of this function. But if we actually look at the gradient, if we look at the function that we're taking the gradient of, it looks like a mess. And so what we're going to do is we're going to have to find a training routine that's somehow smooth, right? That looks not like that. And so we're going to take a pretty like brutish approach to this problem. And what we're actually going to do is just find some way to quantify smoothness, and then we'll just like grid search to find a smooth learning algorithm. Okay. The only thing we need to do this is some way of quantifying what it means to be a smooth learning algorithm. Right? And so if we think back to like optimization theory, what we're actually after is like beta smoothness, which is essentially sort of how close your actual model behavior is to your first order prediction of model behavior. Right? And generally, functions that satisfy this property are smooth, and like gradients are nice, and you can do good things with them. Okay, so what we're really after is this. Unfortunately, we can't really compute this because of several reasons. So one is that it's really hard to compute the max. The other reason is that it's actually pretty hard to just interpret what's going on in this quantity. Like if I measure this and then I tell you it's 200, which happened to us, like I just didn't know what to do with that. And the final thing is that this definition actually relies on having sort of the full Jacobian of the training of like the model parameters with respect to the metaparameters. And that just isn't going to work based on the algorithm that I just showed you. We can only compute gradients of scalar outputs. Okay. So I'm going to skip over sort of our procedure for simplifying this. But I want sort of the high-level takeaway here is that we're going to come up with some metric that we called meta-smoothness. And the nice thing about this metric is that it goes from -1 to 1. We can compute it really easily. It actually doesn't rely on even like applying our fancy algorithm, so we can compute it pretty cheaply. And what it's going to do is allow us to basically grid search to find a smooth learning algorithm. Okay, so what's happening here is each of these dots is just like a different hyperparameter setup for the learning algorithm. Like we changed the batch size, we played with like gradient scaling, we played with gradient clipping, with like batch norm placement. Each one of these dots is a different training setup, and the x-axis here is like the smoothness notion that I just told you about, this like meta-smoothness notion. Okay, so intuitively we're looking for things that are closer to the right here. And this graph actually serves as a really good sanity check, because what I'm showing you here is actually this measure of smoothness plotted against how good we are at optimizing, how useful our gradients are for actually optimizing the objective. And so what we see is that like there's a pretty clear trend between these two. And if we sort of select one point that looks pretty smooth and we visualize the corresponding loss landscape, what we see is that like things look much nicer and much more amenable to optimization.
Have you considered using regularization over Z, like usually like L2 induce smoothness?
Yeah, we have not. I can list a bunch of other things we have not considered at the end, but I think there's tons of stuff to do here. And so just what's happening under the hood is there's like a lot of things you can do to increase smoothness. And these basically just look like what super large-scale training people do to stabilize training, we have to do to get meta-smooth learning algorithms. Okay, now, I think one question that I would have if I was looking at this talk is that I spent maybe the first 80% of the talk telling you about how you tell me your learning algorithm and I will optimize the meta parameter for you. And now I am telling you that you have to actually use this smooth version of the learning algorithm. So what gives? And the key property here that we find, which just happens to be true and kind of saves the day, is the fact that for any learning algorithm, even if that learning algorithm itself is non-smooth, we can often find a super close-by smooth learning algorithm, apply our optimization procedure there, and then transfer back the final result to the original non-smooth learning algorithm. Okay? And if this were not true, then the poisoning stuff would maybe be a little bit less exciting. Okay. So that's it for the two challenges. Are there any questions about, what happened here so far before I maybe offer 5 minutes of thoughts? Yes?
I have a very naive question. So I'm wondering whether, do you think that the fact that you have some gain in terms of accuracy is due to the fact that you actually select the training data, or simply because you consider a smooth version of the non?
Oh, that's a great question. Actually, the smoothing of the learning algorithm tends to hurt accuracy a little bit. We more than make up the difference by selecting the data or by actually doing this optimization, but there does seem to be a slight trade-off between smoothness and accuracy, at least in the way we've done it. Yes?
Slide. I didn't get how you selected the one in 006. Did you literally went through every possible configuration, computed this meta smoothness and the objective, and then you...
Oh, great question. In reality, we actually don't ever compute this axis. This is just for you as the audience to be convinced that our metric is good. But really what we do is just search along this way and pick the point with the highest x value.
So basically you need to go through all possible hyperparameter settings where, let's say, I have batch size 10,000 possible options, 10,000 widths, and the Cartesian product of those, and then you select the optimal of those.
In reality, not really, because most of, for example, these tricks that I just showed you are actually pretty well-known tricks in general, just for increasing training stability. So I think the general takeaway is you need to do everything you can to increase training stability, including make the width as big as possible, put batch norm in the right place. This is just kind of showing you as you mess things up by this Cartesian product, the smoothness gets worse. So our actual procedure did not involve a Cartesian product over 1 billion things.
But how are you sure that this heuristic would work on any other distribution?
On any other, sorry.
Because in any other data set, right?
Right, so, yeah, so this, this meta smoothness, are you asking sorry, maybe I lost your question actually. Can you repeat the question?
So you're saying that people have figured out that bigger batch size generally helps, right? But this is only in a handful of problems that we have time, right?
Yeah.
It's not, there's to my knowledge, no solid theoretical proof that this is universally true.
Yeah, absolutely. To some extent, this is going to require some amount of just trial and error in order to find a smooth learning algorithm, for sure. Yes?
Clarify this slide in terms of the previous example. In the datacom case, what are you doing? You're looking at the algorithm they're going to train with, and then you say, okay, let's now do a first phase of searching over meta smoothness to find a different algorithm that's better.
Yeah. In the datacom case specifically, it turns out that the original learning algorithm is already pretty smooth, possibly because it's already large-scale training. But for CFAR, for example, that's exactly what we do. There's first this thing where we train, I don't know, 50 models, figure out what a smooth set of metaparameters are, optimize for those, and then that's it.
Do you think...
you only have a couple more minutes,
okay.
So if you want to finish up and then take questions, you can do that.
The last part is really just the looking forward, so maybe I will do that, because I think this will also maybe address some of the questions. Okay, so the broad goal here, the dream, is really for this to become a pretty standard recipe in machine learning, right? You want to make some design choice, you pick the design choice, you write down your design choice as some kind of meta parameter optimization problem, you find some reasonably smooth training setup, and you optimize. I don't think we're quite there yet. And I'd sort of categorized the three most, in my opinion, most important directions for future work here. One is, I think as some of the questions alluded to, we need a much more systematic way of finding smooth models. I think in doing this, we kind of ignored like this whole literature on like non-smooth optimization and like smoothing, regularization. There's tons, I think, of gain to be had by just looking at some of the literature and applying some of these techniques. The second is in more sort of computationally efficient versions of this, either by using smaller models in order to differentiate or by truncating the training procedure or doing something. And the final way, and sort of the way that I'm maybe most excited about, is that I showed you sort of like the dumbest things you could optimize with gradients through the model training setup, right? You can optimize data weights, sure. You can optimize hyperparameters. We have some examples in the paper. But really, you should imagine that you can optimize like any continuous thing that happens before you train your model. So if you have like a synthetic data generator, and that data generator like generates data that then gets fed into your model training that you then evaluate on, then you can, I don't know, do gradient descent on the parameters of that data generator. Or if you have like some kind of gradient preconditioning, and you want to optimize the actual preconditioning matrix for generalization, you can do that. And so I think we've only really scratched the surface of like what can we continuously parameterize before training in order to improve model behavior. This is a recap. I know I'm just out of time, so I'll let you read this slide and maybe take some questions now. Yeah.
The problem if we train large models is that we are constrained by T and we want to be T as big as possible. So we may want to use your technique on a smaller number of time steps. Do you think that the hyperparameter we find with this metagradient on like smaller scale will extrapolate to larger scale?
That's a great question. I don't know about model scale specifically, but I do know, for example, for data comp, one successful thing that we had to do for the medium setting is instead of like taking the metagradient through the whole model training thing, you can take the metagradient just through like the last k steps of training, where k is some reasonably big number. And those metagradients at least do seem to actually be predictive of what's going to happen. But in general, like tricks like that are going to be needed. And I guess like going even further, you could, instead of optimizing over specific data points or something like that, you could imagine like optimizing the parameters of a policy to select data, right? And then you don't need to apply it to your whole data set. You can just train it on one training set and try to apply it to another.
Thank you for the talk. Maybe I just didn't hear this properly, but for the graph you showed where it's very non-smooth in terms of the meta parameters, is the seed for the model fixed, like for the initial weights?
Yeah.
Okay.
So this is fully deterministic training.
And then would you expect that the function becomes much more smooth if for every point you would average over the seeds?
For sure.
Okay.
Yes. Yeah, definitely.
Okay, so we're going to have a panel now. I think you're going to be on it, right?
Yeah.
Okay, so you can ask him more questions when we get set up. So we'll take a couple minutes to set up, and then we'll do a panel.